The next three sections are fairly simple and straightforward as well. They encompass being able to write what are called isotopic symbols and being able to understand how the periodic table is arranged. And if you can understand those simple concepts, then writing formulas and being able to figure out ions and valence charges and things like that come much simpler to you in the long run. Not that it's easy. I'm not trying to oversimplify things, but it does become easier. So let's start with atomic number, mass number, and isotopes. Let's go there. We're going to start with atomic number, and atomic number simply tells you the number of protons, and that's extremely important because it's the number of protons that are in an element that determine what the element is. For example, carbon is carbon because it has 6 protons. If you take away a proton, it is no longer carbon. If you add extra protons, it is no longer carbon. It is carbon simply because it has 6 protons. So its identity is wrapped up in the number of protons. Therefore, we call the atomic number, and it is symbolized by the letter Z, the number of protons. And then you have the letter A. Now, please do not ask me why. They used the number A for the mass number. I was not around when these men, and they were men, did this. They used the letter A for the mass number and the letter Z for the atomic number. I don't know why they didn't use an A for atomic number, since A starts with atomic. I don't know. But they didn't, and so I'm just going to have to follow those rules that they set forth those 100 years ago plus. So here we go. The mass number tells the number of protons plus neutrons that are in the nucleus. So let's get this straight. If you take the number of things that live in the nucleus, that reside in the nucleus, protons and neutrons together, then you get the mass number. If you only want the number of protons which identify what the element is, then that's the atomic number, which is represented with the letter Z. So those two are very important to the understanding. And then if you put those together with the symbol for the element, which is on the periodic table, and in this case it is represented here with the letter X. Now, there is no X by itself on the periodic table. There's an Xe for xenon, but there is no X by itself on the periodic table. So this is representative of the symbol of the element, which the symbol is always going to be at least one capital letter, or a capital letter and a lowercase letter. And like for sodium, Na, that's Latin for natrium. And so then the A up top here is representative of the mass number, which is never going to be on the periodic table because the number of neutrons can change. Now, according to Dalton's atomic theory, it was always going to be identical. We now know that an atom, the only thing of an atom that is identical is the number of protons. The number of protons of the same element are identical, but it can have different numbers of neutrons, and we're going to talk about that in just a minute. And then you have that number of protons is represented by the letter Z there down at the bottom. So, since Dalton was incorrect when he said that every single atom of every single identical element was exactly the same, we know that's not quite true, but they are the same in that they all have the exact same number of protons. For example, here are 3 what are called isotopes of hydrogen. Now, we know they're all hydrogen because they all have exactly 1 proton. However, the hydrogen that we think of when we think of hydrogen is called protium. Protium. because it only has one thing in its nucleus. A single proton is all that lives in its nucleus. There are no neutrons in there. Then there's called deuterium, and deuterium is quite important in nuclear chemistry because it's what called heavy water that's used in nuclear reactors is made from. It has one proton, of course, because it is hydrogen, but it contains a neutron, a single neutron. Hence, the number 2 up top, which represents the one proton plus the one neutron. And then very, very, very little in the universe is tritium. And it contains the one proton that all hydrogen must have, but it also has 2 neutrons, hence the name tritium. And you can always find the number of protons and neutrons by subtracting. So if you have, this is called, by the way, an isotopic symbol. Oops, I didn't mean to change the screen there. This is called the isotopic symbol. I gotta wait for the screen to go back. Right here, because it contains the atomic number, the mass number. So you can calculate the number of protons and the number of neutrons. This is going to have 92 protons, and by the way, for any neutral atom, the number of protons is also going to be the same as the number of electrons. And then you're going to subtract the the mass number up top minus, so the 238 minus 92 is going to give us our number of neutrons for this isotope of uranium. So this is uranium-238 would be its name. So this is a 6 and this is 14. So there are 146 neutrons in this particular isotope of uranium. In this isotope of uranium, there's still 92 protons, and there are 92 electrons, but there are only 143 neutrons. And their job, remember, the job of the neutrons is to bind or hold those protons in the nucleus. All right? Now you're going to have some sample problems in your textbook, and the sample problems in your textbook are going to be on page 47, I believe, that asks you to find the number of protons and neutrons that are in chlorine 35, chlorine 37, and potassium 41, and carbon 14. So I'm going to let you do those. It shows you the answers, and it shows you how to set them up. Please notice one more thing real quick here before we move on, how that they have written carbon 14, and this is the proper way to write the name. Notice that they've written the mass number behind it. There are two different isotopes of carbon. There's carbon 12, that's the most common carbon that we're used to, and then there is carbon 14. And so to write this carbon 14 as an isotopic symbol, you're going to write carbon, that's the symbol, and then we're going to write the mass number up top, the 14 there, and then you're going to have to look on your periodic table to find the atomic number, because every isotope of carbon is going to have the same atomic number. In this case, since it's carbon, it's going to be 6. All right. And then from that, you can determine how many protons, how many electrons, and how many neutrons is in there. All right? So that takes care of that sample problem 2.2. And so we can move right on to section 2.4. 2.4 talks about the periodic table and how it's arranged. And I'm going to expect you to know that periodic table, and I'm going to expect you to know it very thoroughly. So let's move right on. Here is an example of a periodic table for you. This particular one is color-coded, and I want you to notice that all of the blue are non-metals. This tan color here, in this case, they're called metalloids, and then by far and away, there are more metals, which are the gray color here. So most of the elements that are out there in the world are metals. Over 80% of all of the known elements are metals. Those are the three categories into which the periodic table is divided. Metals, the grays, non-metals, the blues, and then metalloids. I'm also going to expect you to know some other things about the periodic table. For example, I'm going to expect you to know that the horizontal rows across each row on the periodic table are called periods, and they're significant because the elements that fill those rows, they have their electrons that fill the same energy level. So electrons live or fill orbitals that are in that same energy level. Then vertical columns up and down are called groups or families, and that their elements have similar electron configurations, and therefore they have similar chemical properties, because it is how electrons are arranged in an element that determine the element's chemical behavior. And I believe we discussed that in Chapter 1. So you do need to understand that it is how the electrons are arranged that determine both its chemical and its physical properties. I'm going to expect you to know, too, some of the characteristics of metals and nonmetals and metalloids. Metals, for example, are good conductors of both heat and electricity. They also tend to lose electrons when they become ions, which we're going to talk about. I also expect you to know that they tend to be malleable, which means you can hammer them into sheets like tin. You can hammer tin or gold or aluminum into sheets of foil, or you can stretch them into wires like copper wiring for houses. That's called ductile. So those are some properties of metals. And nonmetals are poor conductors of heat and electricity. As a matter of fact, oxygen and some of the other nonmetals like argon are such poor conductors that they're often used for insulators. All right? And then metalloids, they have properties of both metals and nonmetals. And there are only 8 nonmetals, boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine are the only 8 known. So it's not hard to learn those, or at least know where they are. They form like a stair step that separates the metals from the nonmetals on the periodic table. Okay? And then the other most important thing that you need to know from this section is, I really do want you to know the important families from this section, and that would include the alkali metals, which are on the far left side of the periodic table. They are the by far most important family of metals because they are the most active group of metals. And then right beside them in this green in this slide are the alkaline earth metals. They're what your batteries, your Energizer Bunny batteries are made out of. So they're so important as well. They're the second most active of all the metals on the chart. Then on the far right side, the noble gases. They are by far the most important of all of the nonmetals. In fact, they're, in my mind, the most important of all of the elements on the entire chart, because that's what every atom strives to be. They want to be like a noble gas because they're the most stable. Their energy levels are completely full. They're at the end of each row, which means their row or their energy level is completely filled, which makes it incredibly stable. Right next to them are the halogens. And the halogens are by far and away the most active of all of the nonmetals. And that makes sense if you think about it, because they just lack one more electron, just one more, having a completely filled energy level. And boy, they want that electron because they want that filled energy level. That makes them extremely active nonmetals. And then this middle block is called the transition metals. And then it does not show it on this particular slide, but those two rows at the bottom are called the inner transition metals. And I will expect you to know them as well. All right. And that finishes up section 2.4.